I would like to share with you today how to complete a lab, a simulation-based lab on collisions and conservation of momentum. What we're going to turn in, so please read the instructions in the lab. You can download this Word file from our Canvas page. So please do that and then read through it, and we're going to get into the lab. So as you know, momentum is mass times velocity, and we're going to do collisions in one dimension. Collisions could be elastic or not elastic or inelastic. And we're going to also look into partially elastic or partially inelastic collisions. So during lecture, we looked into 100% elastic, 100% inelastic. How do we treat it if it's partially inelastic, not completely elastic and not completely inelastic? How do we deal with that? So I've written some of the theory on here, and I talk here about the coefficient of restitution, which describes partially elastic or inelastic collisions. And the definition of that coefficient of restitution is the relative velocity of the two objects before collision, or their relative velocity after collision divided by their relative velocity before collision. Okay. All right. So you can open the simulation by using this link or going to phet.edu, phet.colorado.edu, and I will go to simulations, physics, and I'm going to uncheck all these boxes here. I'll just leave the one that has to do with motion, and the collision lab is right next to us. So click on the collision lab, and it should open right on the browser. So click on it, and it's going to open. It gives you a few options. We're going to explore one dimension, explore 1D. Okay, so let's look into 1D. Click on it, and there we go. Now, you can choose your collision to be 100% elastic or completely inelastic. So 100%, 0% elastic means it's not elastic, it's inelastic. Okay, and we are going to go to our file here and see what it asks us to do. So we chose the Explore 1D. It says to ask to show more data. So we're going to show more data, and we're going to, this is the position of the objects where they start initially. Those don't matter. What matters for us is the masses and their initial velocities. So let's look at this data table. We're going to start with inelastic. So the slider here is all the way to the left, so it's inelastic. So good. And we're going to choose our masses. The mass on the left is M1 and the mass on the right is M2. So this one here is M1 and this one here is M2, and they are labeled 1 and 2. And so they ask us to choose for the first mass. So we're going to do several calculations here. I'm going to do this one here, the one in the middle, and you will fill in the rest of the table on your own. So I'm going to do just this one here, where it says choose M1 to be 1.5 and M2 to be 2 kilograms. So let's choose it. So this one is 1.5, enter, and this one is, we were asked to put 2 kilograms. Okay, what else? We're asked to put V1 initial to be 3, and so V1 initial to be 3 meters per second. So let's do it. So 3 meters per second, so enter. And we're going to choose V2 initial to be -1. So -1 means it will go towards, so this one will be moving to the right initially at 3 meters per second, and M2 will be moving to the left because it's -1, and I'll put enter. So they will be moving towards each other and they will collide somewhere in the middle. Okay, and all right, so it says here, use the simulation to write down what the initial momentum is and then you calculate it. As you know, momentum is mass times velocity. So let me share my screen here. So momentum is mass times velocity. So the momentum of mass 1, P1 initial, will be M1 V1 initial. Okay, let's write it down. And M1 is 1.5 kilograms and V1 initial is 3. So 1.5 times 3, that gives me 4.5. Units of momentum are kilograms meters per second. So I record here 4.5 kilogram meters per second. That's the calculated. How about the simulation? And by the way, they will match pretty well, very often exactly, actually. So let's see, from the simulation, I will just display what's the momentum. Actually, I will I will display the values. Okay, I'm going to display the values. And by the way, I'm going to remove this reflective border, this one here. I'm going to remove this border. That's okay. And I'm going to display values. So this momentum is 4.5 kilograms, so that it matches. So now we need to do a calculation for P2 initial. P2 initial will be I for initial will be M2 V2 initial. The second mass, which shows it to be 2 kilograms, and its velocity was -1. So its momentum will be -2 kilogram meters per second. So let's record that. So it says the mass is 2 kilograms and the velocity is -1. So the calculated momentum will be -2. What's the momentum from the simulation? It should also read -2. And it says that it's 2. It says absolute value, so it just gives you magnitude. You determine the direction. It's moving to the left, so -2. Now also here I'm asked to find what's the kinetic energy. So remember kinetic energy. So let's put the kinetic energy here for object 1. So K1 initial will be 1/2, right? Remember kinetic energy in general for any object is 1/2 the mass of that object times the speed of that object, or the velocity of the object squared. It's a scalar. So 1/2 M1 V1 initial to the power 2. So I have 1/2. M1 is 1.5, right? First object is 1.5. And V1 is 3 squared. So 3 squared is 9. And then 9 times 1.5, I believe, is 13.5. And when you divide it by 2, you get approximately 6, or you get 6.75. Kinetic energy is in joules, so you get 6.75. Similarly, for number 2, I calculate it. I'm going to calculate it here. And then, and then it says here, what is V final? What's V final? Well, we will run the simulation, let them collide, and then we will see what V final is. So let them collide. Both of them move at a speed of 0.71. Each of them is moving. They get stuck together because it's inelastic. They get stuck together, and they move at a speed of 0.71. So I put here 0.71. All right. So we'll go to the next table to find the totals. So now it says, what is V final? We will just copy this to here, to this table, because it's the same. And now it says, what's the initial momentum? Initial momentum is, and by the way, I will put here K2 initial. We have to calculate it also. It's 1/2 M2 V2 initial squared. And so you will have 1/2. M2 is 2 kilograms. And V2 is -1. When you square it, it becomes +1. And you just get 1 joule. 1 joule. And sorry, I should have written that goes here, right? K2 initial calculated. Okay, so now it says, what is the initial momentum? P initial. P initial, so my system, P initial, consists of 2 masses. So P initial will be P1 initial plus P2 initial. And that's what? Well, it's 4.5 from P1 initial and minus 1 for P2, so I get 2.5 meters. No, not meters per second. It's kilogram meters per second. So let's put here kilogram meters per second. That's the total momentum before the collision initially. What's the total energy before collision? K initial. It's the sum of the two kinetic energies. K1 initial plus K2 initial. So let's add them. 6.75 plus 1, that's 7.75 joules. So the initial total momentum is 2.5, and the initial total kinetic energy is 7.75. So you get 2.5 and then 7.75. So what's the change in momentum? What's the change in momentum? By the way, we got in here, it asks me to calculate also P final. I will get to it in a moment. Right now, actually, what's P final? Well, notice both masses are stuck together, so they're moving as one piece. When they're moving as one piece, so the total mass will be m1 plus m2. So let me put here P final. Both masses moving together, so you get m1 plus m2 because they're stuck together. So 1.5 and 2 kilograms. So first mass is 1.5, the second one is 2, so that's 3.5 kilograms. And then their velocity afterwards, or their speed after the collision, we said it was 0.71. So 0.71. When you multiply 3.5 times 0.71, I have my calculator here. 3.5 times 0.71, I get 2.485. That's approximately 2.49. So I put here 2.49, of course, kilogram meters per second. And so delta P, did momentum change from final to initial? Delta P will be final minus initial. So you get negative 0.01 kilogram meters per second. So this means momentum was conserved because the change is very little, very small compared to their values here. So it's like, what, 1% or so? So it's essentially 100%, it's conserved, which is expected. Momentum will be conserved if there is no external force. Energy will not, because the final energy compared to the initial energy will be different, fairly different. Remember, we got 7.75 for the initial energy. Let's see what we get for the total energy afterwards. Let me use a different color here. Let's see what the final energy is after the collision. K final will be 1/2 mv squared. 1/2. They get stuck together, so they're moving as one unit, and that total mass of the masses is 3.5 m1 plus m2. Their speed after the collision is 0.71, and when you square that, so let's do it. So 0.71 to the power 2 times 3.5 times 1/2, you get 0.882, approximately 0.882. 8.2 joules. Let's see what it was. 0.882, that's right. So notice the final energy is nowhere near the initial. So there was a lot of loss of energy, and it was lost, remember, it was lost as heat during the collision. So that's the change in energy. And you're asked a few questions. Here, was momentum conserved? Was energy conserved? Under what conditions is momentum conserved? So I want you to answer these questions here. So you will hit enter. I will put backspace and maybe use a different color to answer your question. Maybe this one. Was momentum conserved? Yes, it was conserved. Yes. Use complete sentences. Yes, momentum was conserved. And so on. Okay. The next one will be elastic collisions. So let's go to elastic collisions. So I'm going to uh, restart this. It starts with elastic, so that's good. And I'm going to remove this reflective border. Um, I'm going to check values, show more data. And maybe I shouldn't have refreshed from here. I should have refreshed from here because this resets the whole thing. So that's fine though. And by the way, I did one line of calculation, so you will do the rest on your own for the inelastic. For the elastic, so elastic, it looks like this. So we're going to choose, you have different ones. So I started here, the middle one, 1.5 and 2 kilograms. So M1 is 1.5, M2 will be 2 kilograms, and their velocities will be V1 initial will be 3, V2 initial will be minus 3. So V1 initial is 3, and V2 initial is negative 1. Looks like so. So they're going to collide with each other. Okay, and let's start them here. Notice it doesn't matter where they start. This x value does not matter where they start. So when we hit enter, they will collide, and then we will know what happens. So it asks you here to find V1 final and V2 final. It asks you to calculate K initial, K final. It asks you to calculate P1 initial, P1 final. So it asks you to put all of those. So it says record the velocities after the collision. So you will collide them and record the velocities from the simulation. It says perform all the necessary calculations to fill in the rest of the table. So you will calculate K1 initial, I got 0.75, you can double check that. K2 initial was 1, and so on. So let's find what the velocity here is. And by the way, this one should, maybe I should use symbol so it looks like a longer minus sign. Okay, so what should I do? Okay, let's collide them and get the velocities. So, and I'm going to put slow motion because sometimes if they're moving too fast, they will collide too fast and you won't see much. So I'll use slow motion. Slow motion is better, yeah. So V1 is 1.57, but it's moving to the left. So that's negative 1.57. So I put, that's why it's negative 1.57. V2 is 2.53, and it's positive because it's moving to the right. Notice the arrow is to the right, and it's 2.43. The momentum, when you calculate it, you should get 2.36 for this one and 4.86 for this one. This one would be negative 2.36. You can calculate it yourself. So, yeah, you can calculate that on your own. I have this momentum before collision and momentum after collision. It says here negative 2.36. As you can see from the simulation, it's negative. Symbol here just to have that. And then it asks you to find the totals. Once you have the K1 initial, K2 initial, add these two values together to get the final and to get the initial. Notice kinetic energy is conserved now because it's elastic. So the change will be 0, change in momentum will be 0, and you're asked a few questions. All right, finally, you will do this coefficient of restitution, and I ask you to, what if the collision is not exactly 100% elastic? So we're going to first choose the elasticity to be you will do 0, and then you will do, if it's 0, then it's 100% inelastic. So it's an inelastic collision. If E is 1, it's perfectly elastic. So it's elastic. So let me do this one when E is 0.25. And I'm going to choose, it says here, use M1 to be 1 kilogram and M2 to be 2 kilograms. So for the rest of the calculation, let's just refresh. Let's choose this one to be at 0.25. Okay, it's nicely 0.25. This one, we're going to choose it again. They said 1 kilogram. This one will be 2 kilograms. We are going to choose their speeds here for this part will be 1 and minus 1 for the first half of the table. So 1 and minus 1. So this one will be 1. Again, don't worry about the x values. X values just tell you where the position is. That doesn't matter. and this one will be -1, so it is -1, so that's good. And we're going to collide them. And when we collide them, it says what's their relative velocity before the collision. So their relative velocity before collision, v relative absolute value. Relative velocity means they're the difference. So if you're moving towards me with 1 meter per second and I'm moving towards you with 1 meter per second, so we're approaching each other at 2 meters per second, right? So if you have a car moving left at 50 miles an hour, you're going toward that car at 50 miles an hour, you're closing the distance at the rate of 100 miles per hour. So the relative velocity will be, the initial relative velocity will be, so it would be v1 minus v2. So just absolute values here. So let's see, v1 was 1, v2 initially minus v2. v2 was -1, so you just get 2. So that's the relative velocity before collision. It's 2, that's not surprising. So let's see when they collide what their velocities are after the collision. So let them collide and let's see what their velocities are after. I will keep it in slow mode. Notice now both of them are moving to the left, so both of them will have negative velocities. V1 after collision is 0.67, but it's negative because it's to the left, and this one is 0.17 and it's to the left. So let's record them. Negative 0.67 and negative 0.17. What's the relative velocity after collision? Well, you will have negative 0.67 minus, put absolute values here. The other one was, I think 0.17, wasn't it? 0.17, but to the left, so it's negative. So negative 0.17. Minus minus becomes a plus, so this becomes negative 0.5, and the absolute value of 0.5 is of negative 0.5 is 0.5. I forget my units. So that goes here. So 0.5. Now, this coefficient of restitution is a measure of how inelastic the collision is. So it's the different relative velocities after divided by relative velocities before. So let me write it here. So this coefficient of restitution will be V1 final minus V2 final divided by V1 initial minus V2 initial. The line is too long here. So we get equals, let's see what we get. After collision, their relative velocities was 0.5. Before collision, their relative velocity was 2. So we get 0.25, and that is the coefficient of restitution. Okay. If E is 0, if it's 0, then it is inelastic, perfectly inelastic, not elastic. Which makes sense. If they're stuck together, what's their relative velocity afterwards? If they're stuck together, so they're moving both together, they have their relative velocity is 0 because they're both moving at the same rate. So you get the relative velocity after will be 0 divided by the relative velocity before, whatever it is. 0 divided by anything will give me 0. If it's 100% elastic, then you get 1 if it's perfectly elastic. And it could be anything in between also. So it's a number between 0 and 1, this coefficient of restitution between 0 and 1. Unless it's, I mean, it's possible for it to be more than 1. You can ask me why. I mean, you can think of it like if you have like two things just move apart. If you have like some chemical reaction and they're moving apart, then it could be more than 1. And so you will fill in the rest of the table. You're asked to find what the kinetic energy is and so on. You're asked to find to answer the following these questions. So please answer all the questions, and please answer the question right below where it asks you to. Okay, and that's it.